Hello, today I will be doing interference past paper questions. So let's start. Question 1 is the principle of superposition states that a certain quantity is added when two or more waves meet at a point. So what is this quantity? You know that the principle of superposition states that when two or more than two waves meet at a point, the resultant displacement is the sum of individual displacements. So over here, B is the option. Okay. So when two waves meet at point, for example, this is one wave, and this is another wave. If I draw it with red color, then the resultant displacement will be the sum of individual displacements. Let's say this is 1 unit and this is 2. So at this point, the resultant displacement will be 3. The resultant displacement will be 3 and 3. So if I will draw the resultant wave, then it will look like this. Okay. So we will add displacement at particular time. At particular time, the resultant displacement will be the sum of individual displacements. Okay. So over here, displacement is 1 and over here, displacement is 2. So overall displacement, the resultant displacement is 3 for this time interval. Okay. So option B is correct. Two signals approach each other as shown. So two signals are approaching. One is this signal, other is this signal. At one instant, the signals completely overlap. According to the principle of superposition, what is the shape of resulting signal at this instant? So what we have to do, we have to completely overlap these signals, and using principle of superposition, we have to add the individual displacements of wave to get the resultant displacements. Okay. So let's do, for example, if I completely overlap these waves, then this part of wave will be like this. Okay. And then this is the complete overlapping of these two waves. Okay. So up till this point, this is this is central value, and from center to the lower side. So red color is this wave and the black color is this wave. So at this point, if I want to find the resultant displacement up till this point, so these two values are same and both are negative. So resultant displacement up till this point will be, let's say this is 1 minus 1. So the resultant both waves are, the displacements of both waves are -1 till this point. Okay. So the sum will be -2. Okay. So up till this point, the sum will be -2. So let's look at this option. This is the peak is greater and it is from lower side. So it is twice of this up till this point. Then the displacement of one wave is 0 from this point to this point. Displacement of one wave is 0, but the displacement of other wave is, let's say, -1. So the sum of displacement will be -1 plus 0, that will be -1. Okay. So this is -1. So after that, if I look at this region, the displacement is positive, let's say 2 unit, and the displacement of this wave is 0. So if I will add these two, then the displacement will be positive 2. Okay. So this is the resultant displacement of these two waves. So option A is correct. Why option B is incorrect? You can see that the overall displacement of the resultant displacement of these two waves can't be 0. excuse me, because the resultant displacement is only zero when one wave has a positive displacement and the other wave have the same amount of negative displacement. If I will add these two waves, I will get positive displacement will cancel out with the negative displacement. So I will get the displacements of these two waves will cancel each other. So I will get this type of wave. And why C is incorrect? You can see that this interval, during this interval, displacement is more, but after that, one wave has zero displacement, other is negative, so the sum will be like this. So that's why these are also incorrect. Okay, so the basic idea is you have to overlap these waves and you have to find the resultant displacement by adding the individual displacements of two waves. Let's talk about question 3. Waves generators at point X and Y produce water waves of the same wavelength. The wavelength of both waves is same. At point Z, the waves from X have the same amplitude as the wave from Y. Distance XY and XZ are shown. Distance XZ is 24 centimeter, XYZ is 34 centimeters. So the waves from the both sources X and Y travel towards point Z and they overlap at point Z. When the wave generator operate in phase, so the generator are operating in phase, the amplitude of the oscillation at Z is 0. So they interfere destructively at point Z. Okay. So what we have to find, what could be the wavelength of waves? We have to find the wavelength. So you know that if the sources are operating in phase and the amplitude of oscillation at this point is 0, this means that they are interfering destructively. In condition for destructive interference is the path difference. Path difference is the difference between these two paths, that is YZ minus XZ. Okay, YZ minus XZ, this is the path difference, and this path difference should be, if they are operating, if the resultant displacement is 0, then the path difference must be integer multiple of this is the condition for path difference, lambda. So integer multiple of lambda by 2. Okay, so path difference can be half wavelength, path difference can be 3 by 2 wavelength, and path difference can be 5 lambda by 2 if the sources are operating in phase. Okay, but if they are operating out of phase, then the condition for constructive interference, this is condition for destructive interference, and condition for constructive interference, path difference can be 0, path difference can be lambda, 2 lambda, 3 lambda, and so on. If the sources are in phase, then this is condition for destructive interference and this is condition for constructive interference. Okay, so over here they are operating in phase. So but at point Z they interfere destructively because the amplitude of both waves, the resultant amplitude at point Z is 0, so they must interfere destructively, and this is the general condition for destructive interference. N can be any number. N can be a positive whole number. For example, if n is 0, then path difference will be lambda by 2. Okay, 0 plus half lambda, that is lambda by 2. If I put n 1, that will be 3 lambda by 2. If I put in n2, that will be 5 lambda by 2. So n can be 0, 1, 2, 3. Okay. So this is the general condition for destructive interference. Okay. So what we will do over here, the path difference between these two waves is 10. So I will put n plus half lambda equal to 10 because I am given the path difference as 10. So I will check for n0. If I put n0, then I will get lambda by 2 equal to 10. Okay. So lambda in this case will be 20. And you can see there is no option of 20. Then I will put n1. If I put n1, that will be 3 by 2 lambda. In this case, lambda will be 20 by 3. So that is 6.6 something. So this option is also not available. Then I put n3, sorry, n2 in this equation. So 2 plus half lambda, that is 10. So what is the answer? For 5 lambda by 2, that is 10. So 5 lambda is 20. So lambda is 4. Okay. So lambda 4 is available there. So this is when I put n equal to 3. When I put n equal to, sorry, n equal to 2, when I put n equal to 3, I will get for n equal to 3, you can verify the n is lambda is 2.86. So lambda in this case is 4 centimeter. Another way of doing this question is you find path difference, and path difference in this case is 10 centimeter. Okay. Then you divide with this path difference should be should not be integer multiple of lambda. It should be this integer multiple of lambda by 2. In other words, if you will divide this path difference with wavelength, you should not get a whole number. So if I try to divide this path difference with 2, I will get 5. So if I am getting a whole number, then this must be condition of constructive interference. So that's why this is wrong. If I divide 10 by 3, I will get 3 by 0.33. So if I am getting, for example, 5.5, 6.5, 7.5, mean complete wavelengths times 0.5. So then that will be our answer. So if I divide 10 by 4, I will get 2.5. So this is the condition of destructive interference, that is, so if I take lambda as 4, then this path difference is this path difference satisfy this condition. Okay. So this is integer multiple of lambda by 2. Okay. So this is another way of doing this question. Let's do question 4. The diagram shows two sources of waves S1 and S2. The sources oscillate with phase difference of 180. This is very important key point, that what is the initial phase, what is the phase difference between the sources. So they are already out of phase. The sources each generate a wave of wavelength 2 centimeter. So this is wavelength. Each source produces wave that has an amplitude x naught when it reaches at point P. What is the amplitude of oscillation at point P? So what we have to find? We have to find the resultant amplitude at point P, and what are given to us? The sources are already out of phase by 180 degree. This is very important thing. So what we will do? We will do the we will find the path difference, and path difference is the difference of these two paths. The waves from these sources reach at point P from these two different paths. So what is path difference? Path difference will be 13 minus 5, that is 8 centimeter. Okay, so the path difference is 8 centimeter. So if these two sources have already a phase difference of 180°, then the condition for constructive interference is, for constructive interference and destructive conditions changes. So for constructive interference, path difference must be integer multiple of lambda by 2. So path difference must be this for constructive interference. And for destructive interference, path difference must be equal to n lambda. So n is 0, 1, 2, 3. So over here, the wavelength of these two waves, wavelength is 2 centimeter. If I divide this path difference with this 2, what I get 4. Okay, so the path difference is this path difference 8 centimeter is integer multiple of this wavelength. This path difference is equal to 4 lambda. In other words, I can say lambda is 2 and path difference is 8. So I can write the path difference as 4 lambda. And this path difference is integer multiple of lambda. That is the condition of destructive interference. So at point P, they must interfere destructively. So if the amplitude of each wave is x naught, then if they interfere destructively, this means that crest of one wave will overlap the trough of another wave and they have the same amplitude. So the resultant amplitude at this point P will be 0. So option A is correct. So what you have to do, you have to check the phase difference between the sources. If they are in phase, then the condition for constructive interference will be this and destructive interference will be this. If they are out of phase, then the condition for destructive and constructive interference will reverse. So you have to look at this. So you know the path difference and you know the wavelength. So you notice that this path difference is 4 times wavelength. So this is the integer multiple of lambda. So they must interfere destructively as the sources have phase difference of 180°. Okay. So I hope it is clear. Question 5. Two wave sources are oscillating in phase. Again, this is very important. They are oscillating in phase. It's a key word. Each source produces a wave of wavelength lambda. The two waves from the sources meet at point X with a phase difference of 90°. Okay, so two sources produce waves in phase. Each so the waves from both sources meet at point X. For example, this is one source S1, this is another source S2, and at point X, the waves from both sources meet. Okay, so with a phase difference of 90°. So over here, phase difference is equal to 90°. What is the possible difference in distance from the two waves sources at point X? So we have to find the difference between the lengths of path from the both sources. You know that 360° is equal to 360 phase difference is equal to the path difference of one wavelength. Okay, so 360° is equivalent to one wavelength. So 1 degree will be equal to lambda by 360. This is ratio method, and 90° will be lambda by 360 times 90. Okay, so this will be equal to lambda by 4. So if 360° phase difference is equal to one wavelength, then 90° phase difference will be equal to lambda by 4. So that's why B is correct. So question 6 is three three waves shown on each diagram have the same amplitude, frequency, but differ in phase. They are added together to give a resultant wave, in which case the resultant wave is zero. You can see in all diagrams, three waves are overlapping and all three waves have the equal amplitude. Uh, Equal amplitude you can see from the diagram. Each wave have equal amplitude, but they have different phases. So, which option will give you a resultant wave zero? So, if the resultant displacement is zero, then at any point, sum of individual displacement must be zero. So, we must check at the start of all waves. Okay, so the resultant displacement, this wave has displacement positive, and this has zero. This has the equal amount of negative displacement. If I add these three displacement, I will get zero. Okay, zero at this point. Initially, I am checking the displacement at the start point. In option B, the displacement of these two waves is zero, but displacement of this wave is not zero. So if I add these displacements, 0 plus negative displacement, so I will not get a zero displacement. So if at this initial point displacement is not zero, resultant displacement is not zero, so there is no need to check at other points. So I will simply reject this option. If I see at option C, the displacement of this wave is zero, but the displacement of these two waves are negative. So if I will add these two negative displacement, I will get a non-zero value which will be negative. So this option C is also incorrect. And in option D, the displacement of this wave is zero. This is mean position, and we take displacement from this position, and displacements from of these two waves are negative. So if I will add these displacements, 0 plus, for example, minus 1, that will be minus 2, which is non-zero value. So I just eliminated all three options, wrong option, by just checking displacement at the start point. So that's why option A is correct. And you can see at all other points, the displacement of this wave will be zero. For example, if I am checking at this point, and you can see that displacements, sum of displacements of these three waves at all points will be zero. If I'm checking at this point, the one wave have zero displacement, other have the positive displacement, and third have the same negative displacement. So the displacement will be zero. So you can verify at all points that the displacement of these three waves will be zero. So let me do question number 7. And question 7 is noise reduction headphones actively produce their own sound waves in order to cancel out external sound waves. This is the mechanism. They cancel the external sound waves by just producing their own signal. And a microphone is a headphone receives waves of any frequency. A loudspeaker is in the headphones then produces a wave that of that frequency but of a different phase. What is the phase difference between the external sound wave and the wave produced by the loudspeaker in the headphones? So what we want, the resultant wave should be zero because it produces a wave which is out of phase of the original wave to cancel the effect of that wave. So the phase difference between these two waves must be 180 degree. They must have a phase difference of 180 degree to cancel the effect of each other. For example, if this is the sound wave and the microphone headphones produces a sound wave that must have the same amplitude and must be out of phase by 180 degree. So in this case, the resultant wave must be zero. So this was straightforward question. Question 8 is, what is not essential condition for an observable interference pattern to occur between the waves from two sources? So this is a very important condition that is necessary for the interference to be observed. You know that the frequency of two waves, which is not, this is very important, okay? So we have to find the option that is not the necessary condition for interference to be observed. The frequency of two waves must be equal. This is the very important condition. Without, if the two waves will have unequal frequency, then their phase difference will change with time. Okay, so the sources must be coherent, mean their phase difference should be constant with time and it should not be changed. So this is also important condition for interference to be observed. The sources must emit waves of equal amplitude, and this is not necessary condition for the waves to observe their interference. And the waves from the two sources must overlap. Obviously, if the two waves will not overlap, then we will not be able to, they will not interfere and we will not be able to observe interference. So the phase different, the amplitude can be different to observe the interference. For example, if we have this one wave and this is second wave and they have different amplitude, okay, so they have equal wavelength, equal frequency, but different wavelengths. So the resultant amplitude over here will be the sum of these individual amplitudes, and we will get this type of wave. This is, for example, 1 unit, this is 2 units, so the resultant amplitude will be 3 units, and over here minus 3 units. So option C is correct. The diagram shows 4 pairs of waves. In each case, the displacement y is measured at fixed point is plotted against time t. Okay, which pair of waves is not coherent? So for coherent waves, the phase difference should not change with respect to time. They must have constant phase difference. So if a phase difference is changing with time, so at one particular time, we will be having, for example, constructive interference at that time. And after some time, we will be having destructive interference at that time. So we will not be able to observe interference. So for coherent waves, the wavelength of two waves must be same. The frequency of two waves must be same. So you can see in option A, these two waves have the same time period. So this means that they will have the same frequency and same wavelength. So option A is they are coherent waves. Okay, so the phase difference at any particular time will be same, and you can find the phase difference between these two waves, and you can see that is 90 degrees, 1/4 of cycle. And these two waves in option B, in option C, you can see that the frequency of these two waves is not same. The time period of these two waves is not same. This is the time period for this wave, and this is time period for this wave. So they have unequal time period, in other words, unequal frequency, unequal wavelength. So they are not coherent sources. Okay. In option B, they also have the same time period, equal time period. They are out of phase by 180 degree, and at all times they are out of phase. The crest of one wave overlap the trough of another wave, so they are out of phase at all times. So they are coherent waves. Okay. Similarly, in option D, you can check. This is one cycle of this wave. You must be able to identify the one cycle. This is time period. Okay. Then again, the second cycle starts from here. This is second cycle. Uh, you can see that there are few peaks in the wave. The displacement becomes zero, again starts, and again becomes zero. So this is one cycle of these waves. Up till this point, this is one cycle. Then you can see this is second cycle. So similarly, the another wave, this is one cycle. So the time period of these two waves is same. You can check it. So they are coherent waves. So in option C, they are not coherent waves. Okay. Question 10, two waves X and Y have the same frequency. The amplitude of X is 1.5 x naught. Amplitude of Y is 2.5 x naught. The waves meet at point and superpose to form a resultant wave. They have different amplitudes and they meet at a point, so they will interfere. For the resultant wave, what is the ratio of maximum possible intensity to minimum possible intensity? So two waves of different amplitude are meeting at some point, and we have to find the maximum intensity, ratio of maximum intensity to minimum intensity. So we will find the maximum amplitude of these two waves. So first we will see that if they interfere constructively, then they will have the maximum amplitude, and you can see the amplitude of one wave is 2.5 a naught, and the amplitude of other will be 1.5 a naught. And if they interfere constructively, then the crest of one wave will overlap the trough of other, and the resultant amplitude in this case will be the sum of individual displacements. So the amplitude of the resultant wave in this case will be, you can see this is 4 a naught. Okay, in case of constructive interference. So in case of destructive interference, they will have 180-degree phase difference, and they will meet in this way. This is 1.5 x a naught, and this have minus 2.5 a naught. They are interfering destructively. The crest of one wave overlaps with the trough of other wave. So in this case, the resultant amplitude will be, you can see this, in this case, it will have 2.5 minus 1.5, that is 1. Okay. So amplitude over here will be a naught. This is negative a naught. This is positive a naught. So in this case, amplitude will be a naught. So if they are interfering constructively, they will have maximum amplitude of 4 a naught, and if they are interfering destructively, they have amplitude of a naught. So you know that intensity is proportional to the square of amplitude. Okay, so maximum possible intensity, the maximum amplitude is 4 a naught, so that will be square of 4 a naught to the minimum possible amplitude will be, intensity will be when the amplitude is minimum, that is a naught square. So if you will simplify this, you will get 16. So option B is correct. So then both waves meet at point. So we have to find the ratio of maximum possible intensity to the minimum possible intensity. So we will interfere them constructively and destructively to find the maximum amplitude and minimum amplitude. Okay. So if they will interfere constructively, the resultant wave will have amplitude of 4 a naught. If they will interfere destructively, the resultant amplitude will have amplitude of a naught. So intensity is the proportional square of amplitude, proportional to the square of amplitude. So we have to take square of both amplitudes, and then we have to take ratio. So the answer will be 16. Okay, so let's do this question. Two wave pulses traveling towards each other on a long rope. The pulses have the same amplitude, wavelength, and traveling at speed of this. The diagram shows the rope at time t equal to 0. You can see there are two waves and they are traveling in opposite direction with the same speed. Okay, both waves have the same amplitude, you can see, and they are traveling in opposite direction, which diagram shows the rope at time t equal to 3 seconds. Okay, so you know that if we know the speed and we know the speed of wave and how much distance these two waves will cover in 3 seconds, you know that distance is speed into time. So speed is 0.5, time is 3, so they will cover 1.5 meter. Okay, in opposite direction. So this point will be this is distance 1, and this point will be at this point. Okay, so if I draw this wave after 3 seconds, I will have this wave. This is the wave after 3 seconds. Okay, this is this wave, and this wave will also cover a distance of 1.5 meters. So this point will be 1.5, will travel 1.5 meter towards left. So this is 0.5, 1, and 1.5. This point will be here. Okay, so this wave will be, if I draw this with different color, green, this wave will be like this. So both waves will overlap in this way after 3 seconds. So this point will reach to at this point, and the whole wave will be like this. So you have to travel both waves in opposite direction, and you have to move a distance of 1.5 meter. Okay, so this ending point of this wave will be at 5.5 because it has covered a distance of 1.5, and the starting point will be at 6.5. And the starting point of this wave will travel 1.5 meter towards left, and it will be at 5.5, and this point will be at 6.5. So they will overlap in this way. Now, if I had to draw the resultant of these two waves, the resultant of these two waves will look like this, because they interfere constructively. The amplitudes will increase, and the both waves will look like this. Okay, so the resultant for after 3 seconds, they will have this type of resultant that will be from 5.5 to 6.5. So option A is incorrect, option B is incorrect. You can see option C is correct for this option. This is not possible. So this was the basic idea that how you will overlap these two waves after 3 seconds. Okay, thank you so much.